circuits and electromagnetism. We will combine a lot of applications. Yeah, so let's start. So first, Happy New Year, everyone. Yeah, welcome back. Hope you are having a great week. And we have a quick survey about course offerings. If you have already filled out, no worries. We will give you a little bit of time. This is about next year. The staff, Mr. Nauman and Ms. Seamer is considering a key change, adding physics 2. So yeah, we would love to have your opinions. So it's in the chat now. So it should be a quick survey. So if you're a senior, I think, do we have seniors here? No, I don't think. I'm the only one. Yeah, it shouldn't concern me.
Hey, Alan, you might also, or I can mention that part of the reason, motivation for this is that waves and circuits have been eliminated from physics 1, right? And so the only way you could get, well, you wouldn't get waves anyway, but circuits, you'd have to get it through physics C. And so
right.
Waves and circuits would be offered by physics 2.
Okay. Yeah, so really that's what we will partially cover today, and the fun stuff. So I think we can move on. So for this semester, we will have some topics: electromagnetism, mechanics, thermodynamics, particle physics, and we will revisit quantum mechanics as well. And then we have a final summary of theory of all matter. And today, the first one is circuit, and it's just a closed path around which current can flow. And to make them flow, of course, it needs to be a closed path. We need a voltage source, and then other components common are resistors, capacitors, inductors, and inductors are concerning concerning magnetism, and also there are if you look at it in a charge way, you can induct with other source of charge. And then the key concepts here are currents, resistance, voltage, capacitance, inductance, and today we'll cover them with some examples in real life.
All right, so we have the fundamental principle of current, which is actually the SI unit of electromagnetism. It refers to the flow of electrons through a conductor, right? And so this is the very formal definition of current. This is how people decided, well, what is current? And they give the example of 2 straight parallel conductors, infinite length, placed 1 meter apart in a vacuum, and it will produce a force 2 times 10 to the minus 7th Newton per meter. This is like the human-made like a standard, right? The SI unit that we use. And so this is like a quick visual of that. You have your infinite conductors right here placed 1 meter apart, and there will be an electromagnetic force of 2 times 10 to the negative 7th Newton between them. Next, we're going to quickly review Coulomb's law and electric field for the next topic. If you remember, we were covering this a few sessions ago. And here we have the Coulomb's law. We can see that basically the force is proportional to like the 2 charges divided by the separation between them squared, right? And so here you can look at like the electric field is where we divide out the charge. And so for a positive charge, you can see the lines of electric potential going away from the charge, diverging away. And over at the bottom, you can see for the negative charge, the lines of electric potential are going like inwards. And so now we introduce the principle of voltage. Voltage is defined as a difference in electric potential. You don't have to understand like the integral here, but like look at on the left side, we have a difference, right? This is the difference in electric potential on the left side. And on the right side, we're basically taking like tiny pieces of the path, right? So this is like 3 different times you have the charge Q, and you're looking at the electric field along the path. It's using something called the dot product, but you're basically looking at how like the electric field is working along the path. And there's like a source, and the source is what's producing the electric field here, which will push the charge, and the charge is like constrained along the path from A to B, along the points A to B. So a misconception about voltage, some people think that voltage is a force. It's not a force, it's an electric potential. We have a different term that's electromotive force, which is also not an actual force, it's a misnomer, but it's working against the electric potential in a battery. We'll explore that in a little more detail. It's defined as a unit work per unit charge. And next, we introduce the topic of resistance after current and voltage. Resistance is actually about an property of materials. Resistance is measured in ohms, and it depends on the resistivity, which is internal property, which is ohms per meter. And so we see the formula here is this resistivity, the internal property, times the length divided by the cross-sectional area. And using Ohm's law, we can also say that it's voltage divided by current, which is a very important fact. And here we can see that electric insulators have high resistance, whereas electric conductors like metal have low resistance, right? As I said, it's an internal property of materials. And so there on the right, you can see like a picture of what we mean by cross-sectional area and length.
So resistance is what the matter offers us. Basically, it's if you have some even wire, there's always resistance. But imagine if the resistance disappears and then something very cool happens. That's when the concept superconductivity comes in, and it's actually possible in real life. But right now, it's just scientists can make it happen at a very low temperature and basically at some very extreme level. But this will change as last year there was some groundbreaking research, which we'll introduce later. But first we see the graph on the left. The green line represents the change of resistivity and just based on time. And so there's a threshold, you see a vertical line there. That's when the material enters the superconductivity phase. And that's also what we talked about last time, the squid device, and that's how basically it behaves. And when the resistance disappear, if we have a metal like on the right, if there's a basically a imagine the electrons is keep running in it, and then there will always it'll follow the Maxwell equation. Basically, it will induct a force, and there will be a magnetic flux, so it'll keep it levitating. Yeah, and that's all because the current would always be running and it wouldn't disappear. And last year, the research was some scientists used, you can see 2 diamonds and crushing their this compound they formed, and they can achieve superconductivity at 15 Celsius. So what they did here is using these anvils to create very large pressure, and before them, the record was negative 70 Celsius, and this pressure and diamond and their compound works like it was very groundbreaking, and yeah, it was some really cool pioneering research.
All right, so now we'll continue to discuss the capacitor. And a capacitor is just like 2 metal plates with a separation, right? And so the idea is that a capacitor will store or release electric potential energy more frequently than a battery, right? So like an example could be the camera, which will store electric potential energy, and then that's kind of released in order to take a photo. It's converted to like light energy, right? And so capacitance is the ratio of charge to electric potential. And so the key equation is C equals Q divided by V. And earlier we looked at the capacitor. Way back, if you remember photoelectric effect, we were thinking about the capacitor, where like light can flow from one plate to the other.
So an application of capacitance or capacitors is basically sensing, and on the right we can see on the top there's neutral capacitance. There are two capacitance, single capacitance plate laid out, and then basically if you approach it, it will change the field, and then the capacitors can detect, the plates can detect. And below there's only one plate, and it'll also follow the same principle. Basically, your finger will create a capacitor with it. And this is used in touchscreen. So on our iPhone and iPads, we have uh, capacitive, capacitive touchscreens, and it will create something like the graph on the left. Yes. So, yeah.
The key electric component is also the inductor, and it essentially will store the electric energy in a magnetic field, right? Remember that we were talking about Faraday's law last time. What does Faraday's law do? If you have like a magnet, right, flowing through a pipe or falling through a pipe, remember that the magnet was slowing down. We were checking out that example earlier, and that's because of Faraday's law, right? Faraday's law allows a current to create magnetic flux, right? And so we have a term called the inductance, which is key property of the inductor, and it's defined to be the ratio of the magnetic flux to the current. And so here you can see the equation of Faraday's law. On the right is the most complicated form, and on the left is kind of the simplest form here. It's essentially the negative change in the magnetic flux with respect to time.
So this concept Rohan just talked about is very useful of like changing from electric signal to magnetic signals, and this is used in wireless charging. And if you have a there's a wireless charger inside it, you can find a coil, and as current running through it, it will induce magnetic flux. And then when it reaches the phone, the flux will be inverted back into uh, current. And this is how wireless charging works. And just combine what we talked about, since we were talking about charging and energy here, just combine what superconductivity means. If you have like large energy transportation, like we have those power like towers on the mountains, and if there's superconductivity, it means very efficient energy transmission, and that's why it's front end research here.
All right, next we will introduce Kirchhoff loop rule. And Kirchhoff loop rule tells you that the sum of the electric potential difference or voltage in a circuit is zero, right? As we go around the circuit, we choose a direction, we can go around a loop in the circuit, and we can see that the sum is zero. And so there's like different rules for different components, right? You have the resistor, which is like you can use Ohm's law there to think about the drop in the electric potential. For a capacitor, there's a slightly different rule. It tells you that the change in the voltage over the change in the time is the current divided by the capacitance. And for an inductor, the voltage is the inductance. Remember we were talking about the inductance is the magnetic flux divided by the current. And we multiply that by the change in the current divided by time, divided by change in time. And so you don't necessarily have to understand exactly what these mean. You might learn a little bit more of this like later on. But this kind of allows us to create like mechanical analogs, right? And the mathematics which we use to talk about RLC circuits is the same mathematics that governs this spring mass dampener system, for example. which you might be familiar if you studied like physics and differential equations. And so an RLC circuit is just a circuit with resistors, capacitors, and inductors. And we also talk about the Kirchhoff junction rule, which tells you that the sum of the currents into and out of a junction are equal. And so you can see like at point A, there's like a junction, which basically means that the current is just splitting into two places or three places or two or more places. So if you have like 5 amps here, and then this second branch has 2 amps, then this one has 5.5 minus 2 amps or 3.5 amps, right? So the Kirchhoff junction rule is a very cool tool for analyzing different kinds of circuits. And we also have the concept of series and parallel circuits. I'm sure you guys are familiar with these. Series circuits are when components are arranged along a single path, and parallel circuits, the components can be arranged around multiple branches or multiple paths, right? And so the key idea is that we just apply the Kirchhoff loop rule and Kirchhoff junction rules to analyze these circuits, right? So in the series circuit, right, we can apply our rule V equals to I times R for the resistor in the series circuit. And so we can think about that. So if we go like from here, right? From here, and we just go around, right? So we can start at the voltage source, we'll call that V. And then we do V minus I times R1, because the electric potential is dropping across here, minus I times R2, minus I times R3 is equal to 0, right? We went around the loop, and we were able to find an equation, which allows us to analyze the circuit. And for the parallel, in the parallel case, there's actually 3 loops, right? There's like 1, 2, 5, and 6 is one of the loops. 1, 3, 4, and 6 is a loop. And then 2, 3, 4, and 5 are a loop. And we also have the junction. So we can also apply the Kirchhoff junction rule. So it's just these key principles and knowing when to apply the key principles. So the SI unit, these are the SI units. And in electromagnetism, we know that only the ampere is the SI unit, along with some standard units. And we actually see that everything in electromagnetism, all these quantities here, are basically just comprised of the ampere, kilogram, meter, and second. So that's a very key important point. Next, you'll continue with Lorentz force law. If you guys remember, we were also covering this some time ago. And we have a positive charge Q, and there's like an electric force, right, defined by Coulomb's law. And we also have the magnetic force QV cross B, which you can see over here. And so this is the electromagnetic force law on a moving charge in a magnetic field, subjects like magnetic field and electric field.
So an application of Lorentz force would be in electric motors. So we have a spinning one on the left, but on the right, we can do some Lorentz force cross-section with, or right-hand rules in this graph. So remember is QV cross B or current cross B. So there we have a current that's running through this electric field. Remember it couldn't be in the same direction as it is, or there won't be any cross product. So basically we do the right-hand rule, and then we can find a force exerted on the current. So we have a motor that's spinning here, and as it spins, if it cross over a certain threshold, so if you give it an initial push, it'll just keep on going. That's how one type of electric motor works. And another application is in loudspeaker. So to play sound, we store these informations in our computers, and then we give those speakers instructions through the coils, and there we have electric signals. Then we use magnets, and combine with that, we have a electric field with current running through it. So you can see number 2 there, the red thing, I think, or around the red thing, there's voice coils. And so the current is running through a certain path. And then magnet is it's around it, covered around it. and there will have again a vertical situation, and then there will be force coming outside. So if we control the strength of the both the magnet and the voice coil, we can I don't think magnet, yeah, just the voice coil, we can play sounds and change our information into a vibration of the diaphragm in front. Yeah. And the last one is about railgun. So this one is so I think the reason they make this instead of traditional ones is just more power, and I don't know if um, the usability, durability comes into this, but it's a very new project, and the U.S. Navy is designing it. And on the right bottom, you have a kind of an illustration of it. So the the gun is shooting to the right, and we have L. L means inductors here, and resistance. Basically, they will create a current, and then there will be a field. Um, I think coming out, and if we cross that with the speed, we will have a force that's shooting the projectile to the right.
So onto the formal theory of electromagnetism. So a lot of the equations, the Maxwell's equations governing electromagnetism look very complicated. But we have actually encountered a lot of these as we've been studying electromagnetism, right? The first law is just Gauss's law right here. And it can be used to find the electric field through any surface given the charge enclosure. That can be like a cylindric surface. That can be like spherical surface. So like any surface you can really think of, right? And we can apply Gauss's law. And this part right here, this part you can see like the three integral signs. This part is just the charge enclosed, right? We just phrased it in terms of density here, but it's just the charge enclosed. This second one, Gauss's law for magnetism, tells you that the magnetic field lines will continue through, right? They will continue through the object. And the coolest one, we think, is the Maxwell-Faraday equation, which is Faraday's law of induction, which we're looking through like multiple examples of that this time, which is used in many applications. And so it's responsible for the magnet slowing down in the copper pipe. And here we have, I wasn't able to finish the slide. You can see number 4 is a little bit empty here, but I'll explain this one. This is the Ampere circuit law, Ampere-Maxwell equation. And we were also looking at this two sessions ago, where we were looking at mu naught times the current enclosed and how the current can produce the magnetic fields, right? And magnetic flux. And on the right, we look like in a vacuum, right? You have like electric fields, and you can have a changing electric flux, which also creates magnetic fields. And so that's basically the Maxwell-Ampere equation. And so these equations, along with key facts like the Lorentz force law and Coulomb law, constitute the formal theory of electromagnetism. And so for Maxwell's equations, we can phrase the solutions to them like this, right? So if you look back here, there's a few key variables: electric field, magnetic field, charge density, and current density. And we can kind of see those, right? Like E is electric field, B is magnetic field, this rho is the charge density, and this J is the current density, right? So these 4 key variables are in here. And so you can find like a solution to these equations, right? And phrase them like this, in this form. And there's like linearity that applies. So if that's a solution, then we can multiply each of these variables by alpha, and that will also make another solution, right? And so if your like solution is like a light wave, right, then you can like, there's a superposition principle where you can like add 2 light waves propagating towards each other.
Right, that's it for today, and thank you, everyone.
Do you have any questions?
I have one. Did I unmute myself when we were talking about application?
I think you unmuted yourself.
All right. Okay. That's nice. Yeah. So.
All right, well, if there are no questions, remember that you can always email your questions to VCHS Physics. Is it VCHS or VCS Physics? I think
VCHS.
VCHS Physics at gmail.com. And we will get to you as soon as possible.